And so I'm now going to change the definition of capacitance. And I'm going to change it in the following way. I have two conductors. And these two conductors have the same charge but different polarities. And now the capacitance of this combination of two conductors is the charge on one of them, which is the same, of course, on the charge of the other, except different polarity, divided by the potential difference. So that now is my new definition of capacitance. So you always deal with two objects, not with one in isolation. If you have the charge on one of the two and you divide it by the potential difference between the two. You may say, well, it's a little artificial to have two conductors and one is positively charged and the other has exactly the same amount of negatively charged. Well, it is not so artificial as you may think. Remember then we had this Wimhurst machine which I was cranking and I was charging one plate positive and the other one negative. And without my doing anything, if one becomes positive, the other one becomes negative by exactly the same amount because you cannot create charge out of nothing. So if you charge one thing positive, chances are that something else is charged negative by the same amount, but with opposite polarity. So it's not so artificial that you have two conductors with the same charge, but opposite polarities. So now, we have two conductors there. So if we go to these two parallel plates, the question now is, what is now the capacitance then, according to our new definition of these parallel plates? Well, that capacitance C is the charge on one plate divided by the potential difference between the two plates. And the charge on one plate is sigma A. And the potential difference between the plates is the integral of E dot dl. They are separated there by a distance h. I will change that now to a d, because that's more commonly done, that the separation between plates is d. There was a reason why I didn't want to put a d there, because I didn't want to get you confused, but now there is no confusion. And so the potential difference is the electric field between the plates times the distance d. But E itself is sigma divided by epsilon 0, so we get here sigma divided by epsilon 0 divided by d. I lose my sigma, and so two parallel plates have this as the capacitance. It's linearly proportional with the area of the plates. That's intuitively pleasing. The larger the plate, the more charge you can put on there. And it's inversely proportional with the distance between the plates. The smaller you make the distance, the larger is the capacitance. Well, that goes back to this idea, that the closer A is to B, the larger effect that will have on the capacitance. And if you bring them very close together, this potential will go down, and so the capacitance will go up. So it's not too surprising that you see D here downstairs. The closer you bring the plates together, the higher the capacitance will be.